scenarios? Because obviously if this is the endpoint, that's great, but let's say you get pretty good pressure drop, pretty good heat transfer. What kind of things are going to give you an insight to go, maybe we should try lessen the modulation even if we're getting good enough heat transfer?
For my region where it's going to be completely encompassed, I just want to use the largest possible radius that I would reach as my gauge.
And the next logical step is to do CFD. How would you manipulate the design based on the CFD results that you get?
Alright, I'm gonna share my screen. Yes, so today I'm just gonna go through how we created this differential growth heat exchanger. So first off, we start off with a base, and we are also going to do a couple of things here. First, we set up the spline. So this is really the route that each of the 3 channels are going to take. I have an algorithm being run in the background which tries to detect where along this path I should start increasing the radius, because if I don't increase the radius, the channels are going to have fluids that are not able to flow through it. So to illustrate this, I just want to show the cross-sectional region at the transition areas. So you can see that I start off with 3 channels, and as they go in, they start to converge into each other. So you can see that for these 2 channels, let's call this channel 1 and channel 2, if I don't increase the radius, the fluid is going to end up being blocked, right? So I want to figure out where exactly I should start increasing the radii of the different channels, and then where I should stop increasing the radii. So from this point on, the radii is going to remain relatively constant. So over here, I am going to show you guys a couple of extra previews when I run this algorithm. What I'm really doing here is to simulate where the pipe collides and where the pipe is entirely encompassed within the other pipe. So based on this data, I'm able to formulate, let's say, as my pipe goes along here, maybe I start increasing this pipe at this particular region. So it will start increasing. Then you see that at this point it collides. So now I'm trying to find where exactly it's entirely encompassed in the other pipe. So it's entirely encompassed when it hits this region. Yeah. Likewise, it's going to be done at the top as well. So you can see that this is the region in which it's going to be entirely encompassed. This yellow line is the one that is going to be the bigger pipe, right? The one that encompasses the other pipe. That's why you see that suddenly the radii starts to expand, right? And then when it hits this region is when it stops expanding. So that means from here to here, there's going to be an increase in radii. It's going to be, if you follow my mouse, it's going to look something like this.
So I just want to ask, you're saying obviously there's a transition in the radius. Why in your preview is it the same distance? Is that just purely a representational thing? It's got nothing to do with the actual maths.
Yes, that's representational, because comparing this green colored radii and this red colored radii, I know that up to this point, the radii is going to be consistent and going to be the same all the way up to this point, right? Does that make sense?
Mm-hmm.
So only at this point does my radius, at least for this pipe, start to increase. So let's look at this pipe and this pipe over here, right? Okay, so this is the region that this inner pipe is going to be completely encompassed by this other pipe over here. So this is where I want to stop increasing my radius of this second pipe, because that would lead to pressure drop happening within the pipe. That's why I keep a relatively constant for my region where it's going to be completely encompassed. I just want to use the largest possible radius that I would reach as my gauge.
Another question here.
Yep.
When you're talking about radii, are you assuming that the cross-section is always circular, or is it sometimes non-circular?
Yep. So let me toggle to the other view. So at least for this, I am going to assume that it's going to be a circular region. So you can see that up to this point is going to be circular. So from here, as it transitions to the other shape, because my middle radius is going to be relatively constant, even though the shape is modulated, but at least for area wise, because some goes outward, some goes inwards, I'm going to assume that the cross-sectional region remains the same. So I'm making several assumptions here. primarily that the cross-sectional area is going to be the primary factor for my pressure drop, which may not necessarily be the case, but it's going to be good enough for a first initial guess of the behavior that this diff growth would take.
And is that also the case in the transitional area?
Yes. So that's also the case for the transitional area. I'm primarily looking at the colliding region, which is where my radius would start to expand, and where it's totally encompassed would be the final biggest radius that I would possibly have for each given pipe.
Yeah, so say like the splines that you initially defined, say you move the locations where those splines start, there would be an optimal circle to encompass the other two. I'm just asking whether you're calculating, like, from what you're saying, it's just an arbitrary choice. You're just picking one of the three, but for each setup and for each orientation of where your circles start, there would be one that's preferential to pick to encompass the other two.
I think we just chose it arbitrarily.
Okay.
But of course, if you want to choose it based on some algorithm, you can always do that.
Yeah. I was just asking
Yeah.
if you had or not. Okay.
Yep.
Yeah, looks interesting. I'd actually wonder regarding the differential growth part itself. Is it possible to modulate, like you mentioned earlier, the pressure drop right now is based on surface area alone.
Mm-hmm.
Sorry, the
The
cross-sectional
cross-sectional
area.
surface area,
Yes.
yeah.
So my question was, would it be possible to develop that further so that we can do it based on surface area and real pressure drop calculations, like roughness and things?
Right. I think the next feasible step rather than this would actually to go into CFD. The reason I say this is because to develop more sophisticated equations to use that are more realistic, is going to be more effort compared if we were to use CFD results to kind of govern perhaps pressure drop or whatever we are trying to optimize. Because once we have these different CFD results, we are able to know at certain regions, maybe we have a really high pressure drop. So at this region, maybe we want to modulate the cross-sectional area to account for this in some manner. And this is going to be a more sophisticated approach compared to trying to optimize upon our first initial guess, because all those would still need to be equation based, which may not necessarily translate to being equivalent to real life behavior. So I would say that the next natural approach would be to use CFD.
Okay, so follow-up question from there. Now that you've mentioned that the next logical step is to do CFD, how would you manipulate the design based on the CFD results that you get?
Yeah.
Would you also use the simulation to change the amount of modulation being done on the walls of the pipes?
I think for a different design that would work. Why I wouldn't do this for this particular design is because you see that there's already very little gap between the two regions, right? So there's not much more modulation that you can
No, as in
have.
less modulation, perhaps.
Less modulation. Yes, that's definitely something that is going to be possible if we realize that, let's say thermal heat transfer really reaches a certain threshold and doesn't really improve any further at some point, then there really isn't any need to do any further modification. But what we could also do is to try to experiment with not just a differential growth shape, but a more regular shape. We can use different. One thing that comes to mind is this super shape formulas. So this would be more regular than a differential growth. So perhaps it could yield different results. Yeah. So we could even do something like this for at least for the cross-sectional region by using different shapes here.
Yeah, I mean, on Akhil's comment of what if you wanted to reduce the modulation, if you're saying you're starting here, say at a maximum of your modulation, you've got the most amount. If you were to do an experiment, how would you go about picking, where your start point and end point is? Because obviously, if this is the end point, that's great. But let's say you get pretty good pressure drop, pretty good heat transfer. What kind of things are going to give you an insight to go, maybe we should try lessen the modulation, even if we're getting good enough heat transfer? Because if you start at the maximum, how do you know to go lower and test it?
Right. I think because okay, so how I would approach this to see where exactly is the threshold in which we should stop modulating is because the differential growth is created with different iterations. So the more iterations I have, the more abnormal it's going to look. So if we want to kind of test out the different modulations, we just need to increase this iteration count. The higher the count, the more modulated it is, obviously. Perhaps from 0 to 50 is where you see the most improvement. From 50 to 70, maybe there's marginal improvement, and then from 70 to 200, maybe there's not really much difference. So maybe we can stop at 70, for example.
So we could also run a binary search where you start with a set number, and you could just run it with that instead of just doing it by picking a number and randomly choosing where to move from.
Yes, definitely. I mean, after you created all your different simulations using CFD and you have all these different results, you can just run a quick binary search to see where the results are going to be optimal enough. All right, thank you for joining me in this discussion, and appreciate your time today.
No worries.
Thanks,
Bye-bye.
Cheers.
Marcus.
Bye.
Bye-bye.
Looks cool. Someone, makeup. Where's makeup?
Wow, I feel like in a movie production.